Hi everyone. This video is the solution to example 5, the final example for unit load method. In this case, we have the similar structure as the one we saw in the previous example, but in this particular case, we want to be finding the deflection at point C. And what I want you guys to understand by deflection in this case, I want the total deflection. So what we're going to do in this case is find out the vertical deflection for point C and also the horizontal deflection for point C. And once we find out these two, what we're going to say is that the final deflection is nothing more than the vertical squared plus the horizontal squared, and then we do the square root. Because if we know that point C started here, and if we find out that it's going to move a certain amount to the right, and then it's going to move a certain amount down, we can then say that the total deflection delta, so that's this green part here, is nothing more than the Pythagoras of those two. But okay, the first thing we need to find out is these two deflections. So to do that, we're going to use a real structure and we're going to use two virtual structures. So let's call this virtual number 1 and this one virtual number 2. So the first thing is to define the real one that looks exactly like in the previous example, our original structure with the original load. Now our first virtual structure, we're going to use this one for the horizontal displacement. So we're going to put a load of 1 kilonewton in point C in the horizontal direction, while the structure number 2, so the virtual structure number 2, we're going to use it for the vertical displacement. So we're going to use 1 kilonewton pointing downwards. And in this case, we need to remember that the column has 2 EI, while the beams are going to have just EI as their flexural rigidity. Okay, so similar to the previous case, once we establish our problem, let's calculate all these bending moments. So we need to remember the dimensions are the same as before. So we've done the bending moment for this case. It's going to be a parabola here and then constant all the way to the support. And we know the value of the moment is 1 times 4 times 2. So that's equal to 8 in this case. Now, if we're going to look into the second bending moment diagram, so we know that the moment here has to be 0 because there's nothing causing any sort of bending of this bar. And then we're going to get a reaction of 1 kilonewton here and also a moment reaction here of 1 times 6. So 6 will be the height of the column. So we know that 6 is going to be the value here at the support, and this needs to be going to 0 at the end of the column. So this one here will give me the shear force, which then will give me this slope here of 1. So this is all making sense. Tension on the left side of the column, so this is all looking good. Now, in terms of the last one, so this one is going to look like this. If we know this distance is 4, that's that moment over there. This transfers outside, so this is also 4. And now we know the shear force here is also 0, so this needs to stay constant all the way there to the support. And this is it. So now that we have our real structure and our virtual structure number 1 and virtual structure number 2, we just need to remember that number 1 was for the horizontal and number 2 was for the vertical, this deflection. So now we're ready to go to our table and start calculating our deflection. So we know that our horizontal one is going to be a rectangle times the triangle, that's for the column, divided by EI, plus 0. And 0 because we're going to do this parabola times this diagram, which is 0. So at the end of the day, it's just going to be a square times a triangle. Now, based on the table, square times triangle is square times triangle is 1 over 2 ACL, so we can write that down. And we know 1 over 2, A is going to be the value of on one of them, so let's say 8. The value on the other one is 6, and then the length is also 6. So at the end we know this is going to be 8 times 6 times 3, which is equal to 144 over EI. And we know since this is positive, the load we assumed in the beginning, which goes to the right, stays in that direction. So we know that displacement is going to go to the right, which again has to make sense with the way this structure will behave. Okay, looking good. Now, if we go into the vertical one, it's going to be this diagram, so the real diagram, times the vertical bending moment diagram. So here I realized there was a little mistake, that at the end, we need to divide this, not by EI, but by 2EI, because that's the column. So 2EI. At the end, we don't get 144, but we get 72. That's how much is going to move to the right. Now, if we're going to look into the vertical one, we're going to do Square times square plus triangle times parabola. So square times square. This is for the column, so we divide by 2ei plus parabola times triangle divided by ei. And this is it. So now square times square is ACL. So we're going to do, let's say, ACL divided by 2ei plus, and now parabola times triangle. We have this parabola and this triangle growing in the same direction. Let's just confirm. They are indeed growing in the same direction. So that's 1 over 4 ACL, and this at the end divides by EI. So let's finalize this problem. So AC and L in the case of the rectangles will be 8, 4, and 6. So that's 8 times 4 times 6 divided by 2EI. And at the end, this is 1 over 4. AC and L, we're going to do 8 for the parabola, 4 for the triangle, and then 4 for the span. So 8 times 4 times 4 at the end divided by EI. So we can simplify some of these 4's. And at the end, we get that. We get 96 over EI. That's the column. Plus 32 over EI. At the end, this is equal to 128 over EI. The fact that it's positive means it goes down, which was the direction that we assumed in the beginning. So now we got to a point that we know this moves down 128, but also moves to the right 72. So now we can finalize our final displacement, so square root. And here, this is going to be 128 over EI for the vertical, plus 72 over EI, also squared. At the end, what we get is 147 over EI. And here the direction was going to be somewhat inclined. We could find this angle, but that's not the point in this problem. But it's going to be somewhat like this, because we know that this moves 72 to the right, and then moves 128 down. So we just figured out that this delta here is going to be equal to 147 divided by EI. And this is it. So we figured out another complicated problem using unit load method. And in this particular case, we found the total deflection of a particular point in this structure. So thank you for watching and have a nice day.